and thanks for the microphone. Thanks. My talk is entitled Botnets in 2010, Status Quo and Future Threats. And as Sam introduced during his lengthy introduction, is that I'll talk about some current threats that we see, some things that we saw in the past, and some things that we could expect in the future. Just to give a broad overview of what I'm talking about for the people who are not that familiar with the topic. As I said, the main focus of the talk will be on botnets. So on the next 3 slides, I'll just explain the basic concepts, the basic terminology, so that everyone understands what I'm talking about. Here we see a network. Some of those machines are infected. So on those machines, a piece of malware is running. The attacker somehow managed to install this bot on the machine. The bot itself is some kind of simple program, typically enabling some kind of remote control mechanism. So an attacker can send commands to the machine, which are then executed. The bot is installed via some kind of drive-by download, the exploitation of a remote vulnerability, social engineering, or some other possibilities. So the attacker somehow managed to install the bot on the infected machine. And then the specific aspect of the botnet is that there's this kind of command and control CNC server in the middle, and the CNC server enables the communication protocol. So the attacker, who we see in the upper right corner, can send commands to the CNC server from where they are distributed to the individual bots. The CNC mechanism itself can be either pull or push based. Pull based means that the infected machines periodically query the CNC server for the new commands, and the return value is the new command that should be executed, and then the bots do something. In the push-based setting, the attacker sends a command to the CNC server from where it's pushed to the individual infected machines. So basically, these are the 2 fundamental different communication mechanisms here. And then 2 examples just to explain how this could work is, for example, here's a Ddos attack, so distributed denial of service attack, so where the attacker wants to basically cut the internet connectivity of the victim's machine such that it's not reachable anymore. So he sends the command to the bots then start to send packets to the victim, and the victim is overwhelmed with connection requests, with packets or something, and it's not reachable anymore. So effectively, the victim is off the net. And another thing that's quite common in botnets is propagation. So the attacker wants to compromise other machines, so to grow the botnet, so to infect more machines in the network. In this example, the bot master tells the bots to basically scan the network for other vulnerable machines. So the infected machines start some kind of scanning procedure in order to find other machines that are vulnerable to exploits. And then once a bot finds a vulnerable machine, it exploits the vulnerability and sends a copy of itself to the victim's machine. And then basically the bot propagates from one machine to another. The new machine is then also infected. It receives commands from the CNC server, and it then also starts to propagate further. So this is effectively how botnets grow over time. Okay, after... So the question was whether the bots do this autonomically or just based on commands. So typically they do this based on commands, but there are also bots who do this automatically whenever they have internet connectivity. Okay, for the outline of the talk, the main focus of this talk will be on peer-to-peer botnets, since this is the more interesting aspect, so where there's no central CNC server, but a more distributed one. So each infected machine is also a client and a server within the botnet. In the second part, I'll talk about the whale deck takedown that took place in February 2010, where I and also some other people who are here in this room were involved. I talk about both the legal and the technical aspects, some of the lessons we learned, and then I'll conclude the talk with an overview of what we could expect in the future. So in the past, most work has focused on botnets with the central command and CNC, the central CNC server that I also introduced in the past, because it's pretty easy to mitigate those botnets. You've got one central CNC server. Once the CNC server is taken offline, the whole communication channel breaks down, so the attacker cannot send commands to the bot, bots, and effectively the botnet is basically mitigated since the attacker cannot send any commands to the bots anymore. Those botnets typically use IRC and HTTP-based protocols, but we see also more and more bots that use some kind of custom protocol where they have their own encoding schemes, use other ports or other things. But nevertheless, it's pretty easy to mitigate them once you know where the central CNC server is. There are many actions took place in the past to take down this kind of botnets. There are many automated approaches nowadays to find those CNC servers and then to detect them either on the host or on the network level. So it's not that interesting to deal with those anymore, although they are still the most prevalent ones. So I would guess that probably 80%, 90% or so of the botnets that are out there are botnets with a central CNC server. What we dealt in the past more is those peer-to-peer based botnets. So as I said, those botnets do not have the central CNC server, but the CNC mechanism is distributed such that each infected machine is both a client and a server, and it helps to basically distribute the commands from the attacker to other bots. Most media attention for this kind of networks basically went to Stormworm and Whaledeck, since those were the ones that were able to infect tens or even hundreds of thousands of machines. But there are also other kinds of peer-to-peer botnets out there, for example, Nugash, and some smaller ones, which are interesting actually from a technical perspective, since they implemented some unique communication mechanism. And then the basic question we dealt with in the past is, how can we basically track those botnets? How can we learn more about them in an efficient way? And how can we basically mitigate them in order to stop their propagation? So first I'll talk about Storm, since this is one of the earliest ones that got pretty large. So they managed to infect more than 100,000 machines worldwide. And it was one of the largest botnets back in 2007, 2008. So from a historic perspective, it's probably the interesting one. And actually, the lessons we learned from Storm are also very relevant to what we learned about Whaledeck later on. Storm has a multi-tier architecture, so it doesn't only rely on peer-to-peer as a basic communication protocol, but they also have some static servers, as I'll explain in the next slide. The important part is that they use Kademlia, which is basically a distributed hash table, so also used in many of those file sharing mechanisms, file sharing networks. The basic mechanism is that they use some kind of publish-subscribe based communication. So basically the attacker publishes the command at a specific key within the distributed hash table, and then the individual bots search for this key, and from there they basically retrieve the current command. They also had some static backend servers, then some fast flux domains, and propagation via email and social engineering, which I'll explain in the next couple of slides. So this is the basic overview from a structural point of view, how Storm looked like. So we have on the top infected machines that are behind a NAT device, so they run behind the typical DSL gateway. They don't have a public IP address, and they are typically used in order to send out spam mails or to perform DDoS attacks. So these are actually the dump nodes that the attacker just abuses to get his commands done. Then we have the infected machines with the public IP address, which are used as repeaters. So they are basically just some kind of relay between the infected machines and the actual backend servers, which are used by the attacker to distribute the commands and to collect information and such other critical tasks within the botnet. But the repeaters themselves do not cause any harm, since they are just used to relay commands between the different layers. And within this layer, they also implement the Kademlia, so the actual peer-to-peer component. Then there are some static backend servers, which are run by the attackers. In total, they had about 8 or so servers, typically online, in different networks. They changed this from time to time, but those were the servers where they basically stored the new spam messages that should be sent, or they collected credentials that were stolen by the infected machines, or some other management tasks were basically implemented at the back end. And then we had basically the attacker himself, who used his own machine and basically distributed the commands to the backend servers from where they were pushed to the repeaters and then finally to the spammers. So this multi-tier architecture actually made it pretty resilient to take down efforts. One technique they used is fast flux. So fast flux is something that I'll explain on the next 2 slides, just by an example how this works. The basic idea is that the attacker has switches the mapping between a domain name and the IP address very rapidly. So typically, the mapping between a domain name and an IP address is rather static. So for example, if you resolve sigint.ccc.de, you will always get the same IP address. And whenever you do a lookup, you also get the current TTL, so the time to live, which basically describes how long this mapping between the domain and the IP address is valid. And this is typically in the typically several hours, several days, even several weeks in some cases. With fast flux, what they use is they have a rather low TTL, typically 5 minutes or even below, so that they can easily switch between different IP addresses. And the basic idea is that the attacker can use compromised machines as some kind of proxy. So they basically build some kind of overlay network on top of the compromised machines. And this is something I'll explain on the next slide with some visuals. Here's some example. So the armynext.info was one domain involved in this botnet. And then if you just do a lookup, you see that you get 5 different IP addresses. This mapping is only valid for 5 minutes, not 10 minutes, sorry. And if you do a geo lookup, you see that those IP addresses are all located in different countries within different providers. So it's actually pretty suspicious, because why should one domain resolve to IPs in different countries in different ranges? And actually what happens in the, from the big picture is that we have several infected machines running within the network. These are again just compromised machines. And we have in the back end this kind of mothership which actually hosts all the content. Then we have on the bottom just a normal machine which wants to do an HTTP request to this domain, this armynext.info. So in the first step, it does a DNS lookup. The DNS server basically tells the host that the mapping between this domain is now 1.2.3.4. So the machine just issues an HTTP request, which is relayed from the fastflux agent back to the mothership. So effectively, the fastflux agent is just a simple proxy. It's nothing actually fancy, just relaying HTTP requests back to the mothership. The mothership then basically sends the content back to the fastflux agent. From there, the content is sent to the requesting host, and then it's displayed. So effectively, the user basically just sees that he has established a connection to this 1.3.4 machine, and then basically got from there all the content. But actually, the request was also relayed back to the backend server, which is called the mothership. And then if the machine does the same request some minutes later, so when the TTL has expired, the fastflux network itself has changed. So some machines went offline, some machines came up, effectively because those are just infected machines. So the attacker doesn't have any guarantee that one of the machines will stay online, because the user of the infected machine can just turn it down or something like that. So the machine does a DNS lookup again. This time he obtains another IP address. He sends the request again. The request is relayed back to the mothership. From there, then content is sent again to the fastflux agent, back to the user and displayed. So effectively, we have basically the same setup, but from a network point of view, we have contacted a completely other node, and it's completely transparent from the requesting user that this kind of redirection happened. And so effectively, what they have built is this kind of overlay network, which basically proxies incoming requests back to the backend. And within botnets, this mechanism is typically used in order to have some kind of failover mechanism. So whenever a bot doesn't know any valid peers because he was offline for some time and all the peers he knew are not online anymore, he has some kind of failover mechanism to basically get a pointer to the peer-to-peer network again.
But there is no of this botnet which is using Tor, right?
The question was whether there are botnets that use Tor. So at this point, I don't think so, at least not widely used yet. Probably there are some that do, there's some kind of...
Some CNC servers that are using Tor and, how's it called, Tor reverse server mapping. Sort of node type of style, but they are only very rarely used because they can handle the traffic.
Yeah, that's one of the drawbacks because handling traffic within Tors. But yeah. Okay, here. So the bot knows about one domain that belongs to the botnet, so he does the lookup. The DNS server then tells him the IP address, and this is then the effective entry point to the peer-to-peer network again. So fast flux is some kind of failover mechanism once the bot doesn't know any valid peers anymore. So the question was whether DNSSEC can prevent this kind of abuse. I don't think so, because the operator just changed the mapping, and if he changes the mapping, he can also sign the update, so that shouldn't prevent it. But there are some efforts within within ICANN and some other bodies who do this kind of stuff, who basically want to stop this kind of frequent change of the domain IP mapping. So. DNS will still work because they typically do not switch hundreds or thousands of times per day your mapping, but just a couple of times probably. Yeah, there are some issues that need to be discussed, definitely, yeah.
Actually, they have, like Google is relying on the same technology. They're having small TTL to do load balancing, and so do other services. Like everyone is doing load balancing based on DNS. So there's got to be some means to actually keep this up, and therefore Fastback will also continue working in the future.
Okay, that's right. There are some things like all those content distribution networks, which have also this kind of low TTL and everything, but still they just rely on IPs within the same AS range or something like that. Not all of them, of course, but for example, Google has their own AS where they do all the switching. But I think there will be some technical means to mitigate fast flux in the future, or at least some fast means to basically prevent those domains so that they get shut down. At least my hope. Okay, how are attackers using this kind of botnets? Typically, in the case of Storm and also many other botnets, they just send out spam mails. So there are some, in this case, this was done just over a couple of weeks. We tracked what kind of spam mails they sent. So you see that they sent typically different campaigns targeting different days. For example, here they had some campaign that just lasted a couple of days just for Halloween, where they just sent mails that have this Halloween theme in order to social engineer people to click on the links. They send out stock spam, so they advertised penny stocks. They had some money mule recruitment spam waves. And Kitty was also some kind of social engineering attack where they basically just try to basically trick people into clicking on the link. And this, for example, how the Halloween theme looked like. So the users just got the spam mail, they just clicked on the link, got to this page, and there basically a binary was offered to them, and the attackers also tried some drive-by attacks in order to compromise the browser. And if the victim was not vulnerable to those drive-by domains, they still offered the binary to download. So the victim was also basically infecting himself if he just clicked on it and was then attacked. Yes?
A page like this are those pages on like legal, normal servers or on compromised machines, or where do they host such customer victim entry pages?
Those are basically either they rely on fast flux, so they just advertise the domain within the email, and then if the victim clicks on it, it just relayed through one of the infected machines to the backend. Yeah, that's the typical way. Or they just use compromised machines, depending on what kind of botnet. For example, Coopface just uses compromised machines. So the interesting thing with peer-to-peer botnets is that you can basically crawl the complete network because it's a peer-to-peer network. So this works because each peer knows a couple of peers around him because that's what peer-to-peer is all about. So each machine basically has a peer list which contains IP addresses of other machines that are also infected. So, and let's consider, for example, I know one of those peers. I contact this peer and ask him for his peer list. Then this peer basically tells me, okay, I know these peers. And then I can use this list as the starting point again to query those IPs for their peer list. And if I do this recursively, I will eventually contact every node within the network, at least if the network is connected. So this is an easy way in order to basically recursively crawl the complete network so that you can enumerate all nodes that are currently active. Actually, this is pretty efficient. So crawling Storm, for example, took only about 4 to 5 minutes. So this can be done rather efficiently. And here is a plot over time, also split by geolocation. So you see, for example, in red, this is the upper one, all the machines that run within the US. And you see that typically in the beginning, there were between 5,000 to 10,000 machines online at any given point in time. And we saw peaks of up to 40,000. And this is only the snapshot. So in this point in time when we did the crawling, we saw that many machines online. And effectively, more machines are compromised, but actually we don't have any good measurements in order to say how many machines were infected in total, because that's pretty tough to get to. What you also see is those kind of diurnal patterns. So during the noon hours, you typically see the peak, and during night hours, you see the lower point in time, or point in number of infected machines. So this is because people basically turn off their machine, turn it on again, so you have those diurnal patterns over time. And you see those in all countries. And if you compare, for example, the US to India or to Turkey, you see that there's a shift of a couple of hours because machines in the US are online at another point in time compared to machines in Turkey, for example. And the third aspect I'll talk about is the spam templates. So what typical botnets do nowadays is they use template-based spamming, which means that the bot basically receives a template which specifies how the spam mail that should be sent out should look like. For example, here we see that a received header is, for example, specified. And then we see that the from field actually contains some kind of variable. The to field, there's also some kind of template in there. The subject itself is fixed, and then the date also has some kind of identifier, which basically tells the bot, okay, whenever you want to create a new spam message, use this template, fill in all the variables, and then once you have filled out the template, just send it out. So this basically helps the bot master to be more efficient, since the infected machines handle all this creation of the new spam messages, and so they can effectively spam more efficiently. And so on the top we see how the template looks like. On the bottom, how the actual mail that is constructed looks like. And this is how this template or spam-based or template-based spamming, template-based spamming works nowadays. So this is how basically most of the large botnets basically send out their spam mails. And we'll come back to this point later. For mitigating Storm specifically, and also some other of those peer-to-peer networks, there are some different techniques. The basic theme is that we try to inject announcements into the network. So we join the network and then send messages that do not basically belong to the actual botnet communication, but we try to somehow disrupt the communication channel. There's the typical attack, which is called Sybil attack, basically works in this way, that we announce a large number of peers. We place those peers in such a way into the network that we are basically near each of the infected machines. So in our case, we injected 2 to the power of 24 fake nodes into the network, so quite a few of them. And they were positioned in such a way that we are basically near each of the compromised machines. For us, this didn't work because the network itself was too sparse. But then we tried some other attacks, basically by just polluting. So we were just advertising basically the same keys that also the attacker was advertising, thereby overwriting basically his commands. This actually worked quite efficiently in practice. The only problem is that this is some kind of arms race, which basically prevents to do this disruption efficiently. There was a talk on 25th C3 by Tillman and the other guys from the University of Bonn on Stormfucker, where they actually showed how this can be done efficiently in order to disrupt the complete communication protocol. And they were basically able to disrupt the whole communication protocol within Storm, which is basically the most efficient attack on Storm and basically can be used to mitigate the whole network. Okay, so much for Storm and the different techniques. So fast flux, template-based spamming, and all those spam waves, the social engineering and everything. And now to Whaledeck, which was basically the large botnet in 2009 and now also in 2010. Actually, Whaledeck first emerged about December 28. So it was the successor of Storm, because Storm basically degraded, let's say it that way, because some of the backend servers were taken down in different efforts. So the communication protocol was actually stopped at some point, and then the botnet actually mostly disappeared. And then back in December 28, we saw a new botnet emerging. It's called Whaledeck. It uses basically the similar concept. The only major change is that it now uses HTTP as a protocol to tunnel the traffic between the spamming and the repeaters. But everything, again, is the same. So we have this multi-tier architecture. We have static backend servers, fast flux domains being used for CNC purposes. They use propagation via email and then social engineering, so tricking people into clicking on the links. So from a conceptual point of view, it's actually the same as we saw before. Yes, I'll come to that back later. As you see from the overview picture, it's basically the same. The only major thing that changes is that the spammers and the repeaters now speak HTTP in order to tunnel the CNC communication. But apart from this, everything is the same. They also have this fast flux mechanism in order to have this failback to get back into the network once a peer doesn't know any of the peers anymore. And here's, for example, one indication that it's actually the same group, because they use the same template mechanism. So this is a Whaledeck template. And if you take a look at the different message ID or from, everything was highlighted in red actually here. It's actually the same as we saw before in Storm. So, and since they use the same template language, is one of the indications, they use basically the same protocol and everything. So there are some other hints that it's basically the same group, at least hints, let's say it that way. Okay, then talking about Operation B49, which is basically this takedown effort that took place in February this year. There was preparation for, I wrote here a couple of weeks, but actually a couple of months. So there were many people working on Whaledeck back in 2009, also starting back in 2008 actually. And then at the beginning of 2010, actually Microsoft basically brought together a couple of people in order to basically stop Whaledeck, since basically they wanted to have some kind of case study in order to see how botnets can be taken down nowadays. The whole operation actually consisted of 3 different actions. On the one hand, there was the takedown of the different domains, which was more from a legal point of view interesting, because this was done via a court order. Then the backend servers were taken down, which is more interesting from a technical perspective, since it involved a coordinated action all across the world in order to get those servers down. And then there was also some kind of attack on the peer-to-peer protocol in order to stop the communication protocol. Yes?
The backend servers, weren't they hosted by bulletproof hosting providers, or how was that taken down? Because if it's the static backend server, usually
I'll come back to this in the next couple of slides when I talk about the 3 different actions. There were a lot of partners involved. For example, Microsoft was taking the leading role in order to coordinate everything. There were some people from Microsoft actually led the whole effort. Some people from University of Mannheim, for example, Ben Stock, who's also here. Theo Wehner, that was me. University of Bonn, where Tillman and his colleagues helped. People from Shadow Server, University of Washington, Dave Dietrich, some people from Symantec helped. So there was a lot of coordination going on in the back end where basically many people helped in this kind of operation. The first part, this was interesting more from the legal point of view, was Microsoft basically took or basically collected evidence, quite a lot of evidence actually, and they claimed damages related to spam on Hotmail. So they were able to basically convince the judges that they had actually quite a lot of damage related to Whaledeck, to the spamming, since they had to implement some kind of filtering mechanism and everything, and lots of basically load that they had to handle, so that they actually had damage here. And then they basically collected all those evidence and went to court. What they had with them was a list of 276 domains, some of them listed here, which they basically wanted to take down. Luckily, all of them were hosted within VeriSign, so all ended in .com. So there was luckily only VeriSign who was responsible for this. So this was one of the, let's say, lucky cases here because there was only one registrar involved. Some people from Microsoft here, TJ, I just mentioned him on the slide. He did some excellent work here in order to prepare all the documents. So this was, I think, quite a lot of effort. Everything is actually online. So if you go to noticeofpleadings.com, you get the full documentation, both in English and in Chinese. Chinese because many of the domains were registered on probably fake people in China. As I said, all the court orders and all the basically documentation is available on this website, where you can get a detailed overview of what they did. And this is hundreds of pages of text that they had to prepare for court in order to basically get them into the decision that the domains can be taken down. Actually, I think it took 2 or 3 days until they got the court decision and until everything was implemented. And at this point, actually, basically, VeriSign took down the domains, so they didn't resolve anymore, but they were just, if you wanted to resolve them, you got an X domain. So this part was then effectively mitigated. To the backend servers, which we had the question before, basically they were hosted at different hosters, but the people from Shadow Server, they did quite a lot of work there in order to basically put pressure on the hosters to get them down. They also did this quite and a lot of effort. Typically, they also needed some kind of proof, so some kind of network trace, which basically proved the hoster that the specific server was doing something malicious, and eventually they could get all of them down. There was some kind of arms race where the attackers also brought up some new servers, which had then to be taken down, but the guys from Shadow Server did some excellent work there, and they were able to bring all of them down. And then disrupting the CNC mechanism. This was basically an attack that was also discussed by some other people in the academic community. So Craig Sinclair did some work there. There were lots of discussions also with Ben, who did all the implementation work here in order to basically implement this disruption mechanism. And the idea was basically that our servers were injected into the peer list, so that we basically became some kind of super node within the complete network, so that basically every infected machine just knew our server. That's how you can think of it from a high-level point of view. So that basically within the peer-to-peer network, all the legitimate server were not valid anymore, but all the infected machines just contacted our servers. This was basically done by announcing our machine and having a long peer list where we basically tricked each bot into thinking that we were the only valid servers out there. So we did not execute any commands on the infected machines or anything, because there's a basically thin line from a legal point of view, what you can do, what you can't do. And so therefore we opted basically just to stay at the, I think at the wide side of the line. So not to do any harm to the infected machines, but just let them think that basically the valid CNC servers are not there anymore. In the back end, this took some effort at our side in order to handle all the loads and everything, but this went well. And then from a schematic point of view, the botnet then looked like all the infected machines basically contacted our server, the backend servers were taken down, and so the attacker could effectively not send commands to the bots anymore, so the communication channel was also effectively disrupted. And since also all the domains were taken down, there was also no way for the attacker to easily basically bring back the CNC mechanism. The effect basically helped in order to basically disrupt the CNC communication. So also other people who monitored the network saw that no new peers were within the botnet. And then if you monitor the number of bots over time, you see that it's decreasing, probably because some of the infected machines will be cleaned up and everything. So over time, we'll hopefully see less and less infected machines. But that's also one of the problems. The CNC mechanism is disrupted, but still all the infected machines are out there and the machines are still infected. So the attacker cannot send commands to them anymore, but still the bot software is running on those machines. So how to clean up the machines is still an open question. And perhaps we'll implement some kind of notification system similar to what the configure working group is doing, but still. And as I said, the disruption worked effectively. Some lessons learned in the last couple of minutes. On the one hand, so botnet takedowns have some advantages and also drawbacks. The clear advantage is that the bot masters cannot do any harm anymore, since they cannot send spam mails, they cannot install additional malware on those machines. So this is clearly positive. But there are also some drawbacks, for example, that we lose insights into the network, so we cannot track what the attackers are doing. And presumably the attackers will continue their work. So they will simply basically develop better tools. So we'll feed this kind of arms race so that they will come up with a new design probably in the future. And then basically we need to basically do all the work again, similar to what we saw with Storm, which then evolved to Whaledeck. And then probably you will see something better also in the future again. And the technical means are only part of the puzzle. So it's basically, from a technical point of view, you can do quite a lot. You can do the disruption, you can do things like taking down things, but on the other hand, we also need other views here. For example, in order to take down the bulletproof hosters, we need this kind of social component where people basically can call others and force them to take something down. We had the court order, which helped to put down the domains. So there's lots of collaboration potential or collaboration need actually here. And yes, as I said, it's important basically use or collaborate with others, because probably the next generation botnets, once they use strong crypto, once they use mechanisms like Tor, for example, or hidden servers or some things, then it gets pretty hard to basically track them and to shut them down.
So what more than RSA and AES would you use in strong crypto? Just to use it the right way.
Use it in the right way so that you use basically public key crypto in the right way and not AES where you have the key within the binary.
Are you sure they will really notice that that was the problem?
So if they don't, probably if they don't notice this now, they will learn it in the next iteration or at some point. Okay, just feature work. So actually, Operation B49 was just the start. Actually, within Microsoft, there's the effort of Project Mars, which was announced at CanSec back in March. So basically, within Microsoft, there's quite a lot of effort now going on into tracking other kinds of botnets, also taking them down. So there are many people now aware that this kind of things are going wrong, and then that we need this kind of takedown efforts, and probably there will be some more similar efforts in the future. And then in conclusion, we saw those interesting botnets that used and that show the possibilities of peer-to-peer botnets, but they were not resilient against mitigation efforts. So in each case, there were some kind of attacks that the defender could use in order to disrupt the communication channel. But probably we'll see some kind of evolution in the future where those botnet designs get better and better. And I think Operation B49 was especially interesting from the legal groundwork that was done in order to take down the botnets. So we now have this kind of legal procedure where an ISP or Microsoft or some other entity can just simply go to court and get this kind of court order to do something. So besides the technical means, there's also this legal groundwork now. Okay, thanks a lot for your attention. And the papers, what I talked about, are available on my blog, and also if you just Google for it, you'll see also the work by Tillman and all the other people. Thanks a lot, and then I'm happy to take your questions.
Hi, Torsten. I have a comment you might want to comment yourself on later on, and also a question. So the comment is, although it's not your fault, of course, I find it somewhat problematic to maintain those infrastructures, to keep them up and running in order to, sinkhole the botnet or block the botnet. I mean, because that doesn't scale. But you might want to comment on that. So that's kind of a difficult situation. And the question is, do you think there could be a problem in the future with that kind of research, because there might be institutions that might want to go one step further and actually take over the botnet and use that for their needs or something? I mean, I'm speaking of institutions that don't need somebody else's approval for that.
Yeah, some good points. So on the one hand, of course, this problem of scalability. So if you maintain those sinkholes, if you sinkhole the traffic, you of course have the problem that those infected machines basically contact you all the time. And that's what I also briefly mentioned before. So we still have all those 1,000 machines which are infected with the binary. And how to deal with them is, I think, still an open problem. Because, yeah, there are tens of thousands of machines, especially with Configure, where you have millions of those machines, what to do with them. And then...
It's about responsibility, right? Because you cannot take down this infrastructure now.
Mm-hmm. Yeah, that's true. And yeah, for the second part, what happens, for example, if you would have some kind of buffer overflow within Configure, what would you do with it? That's actually a pretty interesting question. Would you publish this information or not? Actually, I think that's, yeah, I think you can discuss both ways.
So if I understood it correctly, with rather limited resources, you took down the whole peer-to-peer network, basically. In comparison with legal peer-to-peer nets, would it also be possible, or are they better guarded against such attacks? Because I think most peer-to-peer networks believe all clients are somewhat good or something like that.
Yeah, but so in many of the peer-to-peer networks, so in the B9 ones, you also have the possibility of some kind of Sybil attack where people can basically spy on others. Actually, there were some studies, actually one was published, I think 2 or 3 weeks ago by some researchers from France, where they studied, I think within, I don't remember within which network, but they basically spied on the search terms everyone entered within the network or such things. So you can attack all those DHTs, because Sybil attack is one possibility in order to basically disrupt the integrity of the network. So if you just Google for a Sybil attack, you'll find all those papers with the studies.
Could you say a few more words about how to take down the backend servers? It's like you put some pressures on the ISPs and give some evidence, and then bulletproof hosting is not bulletproof at all, or how does it work?
Yeah, so basically, if there's enough pressure, they need to do something, because eventually they would probably call just the police or so to get some cooperation from there. Of course, you cannot not force everyone to do something, but still, if you put enough pressure there, there will be some activities from law enforcement, for example. Yeah. Then, do we have time for one more question, or? Okay, so one last question, and then we can just take it offline.
Were the backend server actually hosted at bulletproof hosters or regular ones? Because
it was mixed.
Hosting...
So some of the hosters were actually, for example, hosted here within Germany within NetDirect, so in Frankfurt. but some of them were also hosted in Russia, for example. So it was mixed all over the world. Okay, then thanks again, and yeah, see you next week.